So recall from our first video that if we have a matrix A that's diagonalized as x d x inverse, that allows us to do some stuff with it. Specifically, if we take a to the k power, it's the same thing as if we took our diagonal matrix D to the kth power and just put it back into the formula. So that allows us to compute powers of matrices really easily. But that even allows us to do even more. So recall from Calc 2 that the function e to the x has what we call a Taylor series. That Taylor series being the power series 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus 1 over 4 factorial times x to the fourth, and so on and so forth. This just keeps going. If we have any real number x, we can plug it in here and we get a result. And that result agrees with what we expect e to the x to be in all cases. Of course, not all Taylor series converge for all x's, but the Taylor series for e to the x does. What we're going to do is we're going to use the same formula, but we're going to replace x with a square matrix A. So we're going to be looking at powers of A. The only difference is that we do need to change out this 1 to be the identity matrix so that we're not adding just a single number to matrices. We don't have a definition for that. So we're going to call the matrix exponential, or the exponential of A, which we'll just say is e to the A, is the result of that series. Of course, that seems like it would be a nightmare to compute in general, but that's why we care so much about, or at least while we're bringing this up, after we know how to diagonalize matrices. Because what is the exponential of a diagonal matrix? If we have a diagonal matrix with diagonal elements lambda 1 through lambda n, its exponential is really easy. It's just e to the lambda 1 through e to the lambda n on the diagonal. Just the same way that a diagonal matrix to a power is just all those diagonal elements to that same power. The exponential is just e to each of those diagonal elements on a diagonal. Really simple. And then, if we're looking for e to the a, because we have this formula here, what can we do? We can, well, I'm going to go ahead and write out the formula. I can replace my a with x d x inverse, my a squared with x d squared x inverse, and so on and so forth. And in fact, I'm going to go ahead and change out I. Remember, I is just, you can just say is x times I times x inverse, because the x times x inverse turns into the identity matrix. But it'll be useful to have in that form for the next step. And so on and so forth. So the idea here is that every single term in this has an x in front and an x inverse in the back. So let's factor that all out. We'll factor out x at the beginning, and x inverse at the end. And in the middle here, well, we have the I that's in here. We have the d that's in here. We have the 1 over 2 factorial times d squared. We have the 1 over 3 factorial times d cubed, and so on and so forth. We just actually get exactly the same kind of series that we have here, but for d instead of a. So this is x times e to the d times x inverse. So if we have a diagonal matrix A, we can, once we know that a diagonal matrix has a very nice exponential, we can just use that formula to compute the exponential for A. So let's go ahead and do some examples of that. Now, I should note here before we move on that defective matrices can have an exponential. In fact, every matrix has an exponential. This series always converges for any matrix A, but it's just not as easy to calculate. We'll look at a couple examples of that, but first I want to do some ones that we do know how to do. So here, this is from problem 31. This is not on your homework. You're going to be looking at some parts of problem 32, which are going to use this, and you'll get into how you're going to use that later on, either in this video or the next one, depending on how long this actually takes. But the idea here is that we still need to be able to diagonalize these, or not diagonalize. Diagonalization will be part of it, but we want to find the exponential. Is what we want. So we want to find the exponential for this matrix. That means we need to diagonalize it. So if this was a diagonal matrix, that'd be a simple question, but since it's not, we need to actually go through the process. So we'll take each of our diagonal elements and subtract lambda from them. Go ahead and take that determinant. If we expand this whole thing out, we end up with lambda squared minus lambda, which is just lambda times lambda minus 1. So here, because this has to equal 0, our eigenvalues are going to be 0 and 1, which already tells us this is diagonalizable, so we're not going to run into any issues. Go ahead and start with 0. This will be our lambda 1 is 0, which of course just means that we're going to take our original matrix and use row operations. Go ahead and divide that first row by negative 1, and of course it cancels out the second row. And then that means my x1, if I pick 2 for my second variable, I'm going to be left with a negative 1 for my first variable. Lambda 2 is going to be 1. Means I subtract 1 from each of our diagonal elements. So we have a negative 3 and a 2. Again, let's just divide the first row by negative 1, and that cancels out the second row. So my x2, for the same way, I'm going to pick 3 for my second variable, and I'll get negative 1 for my first variable. So here, my d, remember my diagonal elements are my eigenvalues. I'm going to put the lambda 1 first and then lambda 2, so 0, 1 is my diagonal elements, 0 everywhere else. My x is going to be the eigenvectors in the same order. So negative 1, 2 is my first column, negative 1, 3 is my second column. And here I'm actually going to want to know what is x inverse. And we're just going to compute this directly. We're going to take the matrix x that's in front of us, we're just going to compute it. So we'll go ahead and look at what's the adjoint. So the adjoint corresponding to this negative 1 is just the determinant of the 3 that we have there. So we have a 3 there. Similar things for the 3 here, we just get the negative 1 that we have there. And then for here, well, we get the determinant of this part, but then we have to transpose it later, and we have to multiply it by a negative 1 because it's in this position. So actually, we end up with a negative 2 here, and this negative 1 becomes a positive 1 there. But we're not quite done. We do actually need to deal with the determinant. The determinant of this matrix is just negative 1. So it's the negative of this matrix. Or in other words, we're ultimately going to get negative 3, negative 1, 2, 1. That's our inverse. Not as bad as it could have been. We want to compute our exponential e to the a, and we know that's going to be x times e to the d times x inverse. That means we're going to take this matrix times e to the d. Remember, e to the d, we take our diagonal elements of 0 and 1 and take e to that power. So e to the 0 power is 1. These stay at zeros. E to the first power is e. So we do have an e showing up in here. Then we take our x inverse, and it's just a matter of multiplying these three matrices together. I'm going to go ahead and multiply the second two together first. So I'm going to leave this matrix alone for the moment. But I have, take my row by a column. So 1 times negative 3 plus 0 times 2. So we have a negative 3. Same thing here, we get a negative 1. Then this row times the column. So 0 times negative 3. Then we have 2 times e. Same kind of thing here, we have a 1 times e. Another way to look at this is that this is actually an elementary matrix that multiplies the second row by the e when you multiply it on this side, if you want to think of it that way. So this is just this same matrix is with multiply the bottom row by e. Of course, this product here is a little bit more complicated. We do actually have to work it out. We have the row by column, so we actually have a 3 minus 2e. Then we have that row times that column, so we have a 1 minus e. Then we have row by column, so we have a negative 6, then plus 6e. I'm going to put the 6e first. And then finally we have a negative 2 plus a 3e. Again, I'm going to put the 3e first. There's not really much more simplification we can do there, unless you want to actually write them out as decimals. But that is our exponential for a. It's this matrix here. Okay. Let's move up. Got a 3 by 3. But that doesn't actually change our process. It just means a little bit more work. We need to find what are the eigenvalues of this matrix. So I have 1 minus lambda. We have a negative 1 minus lambda and a 1 minus lambda. This is a 1, 1. We have a negative 1 and negative 1, and a 1 and 1. I'm going to skip some of the steps of actually working this out. Hopefully by this point you do know how to do determinants. We've been doing those quite a bit. But eventually you'll get that this is negative lambda cubed plus lambda squared. Or in other words, if we factor out negative lambda squared, we get lambda minus 1. So similar to what we had in a previous problem, we do have a repeated eigenvalue. We have 0 and 1 with the 0 being repeated. Let's actually go ahead and work with the non-repeated. Oops. So start with the non-repeated one. So we'll say lambda 1 is 1. We'll go ahead and subtract 1 from our diagonal elements. And then leave everything else alone. Go ahead and use row operations. I'm going to go ahead and put the 1, 1, 0 as my first row. Use that to cancel out these. And I'll be left with a 1, 1 here and a 0, 0 here after some work. That means if I pick 1 for my third variable, that's going to force a negative 1 for my second variable. But then the negative 1 for the second variable forces a 1 for my first variable. So this is an eigenvector corresponding to 1. My second eigenvalue, and in fact my third eigenvalue, assuming that this actually does work out nicely, are both going to be 0. Which means I'm going to take my original matrix, and I'm going to do row operations. But again, similar to what we did previously in another video, this first row is just multiplied by various numbers to get the second and third row. I mean, actually, the first and third row are exactly the same. And we just take -1 times it to get the second row. So really, we just cancel out both of those rows. And so this will actually lead us to be able to do this using a diagonalization. I can pick 1, 0 and 0, 1 for my second and third variables. That will force a -1 for both of the first variables in each case, but these are independent vectors, and that's the key to all of this. So here, my D, my diagonal matrix, is going to have diagonal elements of 1, 0, 0, with zeros everywhere else. My X is going to be made up of these three vectors over here. So 1, -1, 1, -1, 1, 0, and -1, 0, 1. Of course, we do need to find what X inverse is to actually do this. And I'm going to just go ahead and write down the inverse. I'll let you figure out how to find it yourself. But the first row will be 1, 1, 1. Second row will be 1, 2, 1. And our third row is -1, -1, 0. That means we can take e to the a to be x times e to the d times x inverse. This is our x. Go ahead and write that in here. E to the d, we're going to take the diagonal elements of d and raise them, take e to those powers. So e to the first power is e to the 0th power is 1, and e to the 0th power is 1. And then we have our x inverse. Get to go through all the steps of multiplying this out. Again, I'm going to multiply the second to first. So leave this first matrix alone. And you can actually think of this as this is the elementary matrix that multiplies the first row by e. So really, I'm just going to take this matrix and replace all the 1s with an e, on the first row at least. And then we get to multiply all those together, and the result that we get leaves an e here, a 1 minus e here, an e minus 1 here, an e minus 1, a 2 minus e, an e minus 1, an e minus 1, a 1 minus e, and an e. So leave that to you to actually do that matrix multiplication and verify that I did that correctly, but that is the result that I got. So we have our exponential for that particular matrix. Now let's look at this one. It looks a lot simpler than the previous ones. We actually don't have much going on in this matrix. So, and this is actually not from the book. I brought this one up myself. But let's actually try to find the exponential. So, we'll just start the same way we did before. I guess we're calling this A. So, subtract lambda from each of our diagonal elements. If we multiply this out, we get negative lambda times negative lambda, or lambda squared, minus 0. And so what do we have here? If this equals 0, then lambda has to be 0. So our lambda 1 and our lambda 2 have to be 0. But there's not really row operations to do. This is really as simple as it can get. And what does this tell us about our solutions? If we set this times a vector equal to 0, what kind of form does that vector have to have? Well, we can get x1 is, well, first of all, the 1 here forces the second variable to be 0. Our first variable can be whatever it wants to be. We'll just set it equal to 1. But that means that every vector in the null space of this matrix is, in fact, a multiple of this. We do not have another independent eigenvector. This matrix is defective. And that might seem like a big problem. In fact, it very much could be a big problem if we don't know too much about this matrix. But we do get a little bit lucky here. Lucky in quotation marks because, well, obviously I picked one that wouldn't be too bad. The fact is that if we take A and we multiply it to itself, we get the 0 vector. Or not 0 vector, the 0 matrix. All zeros. We call such a matrix a nilpotent matrix. Not that you need to remember that. But the point is that once we square it, we have all zeros. If we take this to any higher power, a to the third power, we'll just be multiplying this matrix, the 0 matrix, to a again. Well, that's still going to be the 0 matrix. All powers of a from 2 onwards are zeros. Which means that if we do want to calculate e to the a, it's going to be the identity matrix plus a, just following our formula, and so on, with this being 0, that being 0, and everything else past that point being 0. The only thing that we're left with is I plus a. So what do we have? Well, I is 1, 0, 0, 1. A is 0, 1, 0, 0. Adding those together, we get 1, 1, 0, 1. It's just that simple, as long as we have these nilpotent matrices. There are definitely defective matrices that are not, that do not have this form where the power of it eventually equals 0. So it's not always as easy as this. In fact, if we look at this matrix here, 1, 1, 0, 1, that matrix is defective as well. And in fact, it never has this property. If we actually do want to find the exponential of this matrix, we end up having to calculate this entire power series. It's a fair amount of work, but it's possible to do. And it turns out that this matrix, if I call this maybe off to the side here, let's call that B, just have a different letter for it. E to the B ends up being EE0E. And that's not straightforward to find. So, not gonna actually work that out for you. Just be aware that it did take me some work to actually compute that myself. Alright, so I'm going to leave it here. We're going to actually, in the next video, actually apply this idea. So we've been talking about this exponential as if it's something to actually work with, but why do we care about it? It seems like an odd thing to really care about. But it does actually relate back to what we were talking about in 6.2, back to our systems of differential equations. So we'll get to that then, and I'll see you in the next video.